Hey everybody, just want to do a quick lecture about competition. And so let me get the slide set up here. All right, so this is book chapter 14, competition. And so the key concepts or takeaways from this chapter are the competition can be direct or indirect, it can vary in its intensity, and it can occur between similar or dissimilar species. Also, competing species are more likely to coexist when they use resources in different ways. Next is competitive interactions can be modeled using the logistic equation, and the outcome of competition can be altered by the physical environment, such as disturbance and also through predation. So, a few terms. Competition is simply non-trophic interaction between individuals of two or more species in which all species are negatively affected by their shared use of a resource. And then there are both interspecific and intraspecific competition. Interspecific, of course, is between members of different species, while intraspecific is between individuals of the same species. Resources are components of the environment that are required by a species, and those can be food, water, light, space, etc. And then the fundamental and realized niche. So the fundamental niche is the full set of resources plus other biotic and abiotic requirements of the species, while the realized niche is that niche, the component of the fundamental niche that is restricted due to its species interactions. And so if we take a look, you can see the figure up here on in the upper bit here, upper part of the screen is the fundamental niche, and so this species one's fundamental niche occupies this whole area where the blue circle is, and so in this situation there's just two resources that are being considered. And so if we look at the panel next to it, panel B, you'll see that species one's realized niche is actually quite a bit smaller because there's this competition that gets where the species get squeezed by these other species, and so the species space gets compromised and gets shrunk. And then down in the bottom, this figure is, I think I may have shown this figure before, but this is Grand Prismatic Hot Spring in Yellowstone National Park, and you can see these different colors where these are the different colors in there are actually communities of bacteria and archaea, and those are competing with one another, and the actual distinct colors that you see are due to variations in temperature. And so the species sort of separate their, or the communities that make up the species that make up the communities sort of separate their niche space based on thermal tolerances and their evolution towards being more well adapted to those thermal tolerances. So general features of competition, species may compete indirectly by exploitative competition. In other words, individuals reduce the supply of a resource that they use. And then species may also compete directly by interference competition. In this situation, one species directly interferes with the ability of its competitors to use a limited resource. So quick sort of funny example, exploitative competition would be if you are both drinking out of a straw, and so you're sharing the resource, but you're not directly competing against that person in a sense. All right, and then interference competition would be when you reach over and I know these two individuals aren't pinching each other's straw, the other person's straw, but if you reached over and pinched the person sharing the cup with you, if you pinch their straw, so that would be interference competition. Interference competition in plants is also something that is quite prevalent in this situation. Individuals, one species grow on or shade other species, reducing access to light. So kudzu is a good example. And then allelopathy. And in this situation, plants of one species release toxins that can actually harm other species. And so you see this underneath trees sometimes where there are areas that no other plants grow underneath them. And this is because of the various toxins that are released by the plant that cause the competitive species to be excluded. The example on the right here is a black walnut, and so there's some toxins in the soft tissue of their fruit which actually, incidentally, can be also used as a fish toxin to kill fish, and if you crush them up, and that's sort of a neat aside. Competition also reduces available resources for both species, and abundance of both is reduced to some extent. But the effects of competition are often unequal or asymmetrical. So one species is harmed more than the other. And I have this little cartoon down here, and it's talking about an invasive species with an endless appetite. They can decimate ecosystems, send species into extinction. And those of you, some of you may be familiar with the Asian carp, and so the other fish says, oh, are you talking about the Asian carp? And the report is, no, we're talking about humans. Humans have obviously outcompeted a lot of species and caused their extinction, but the list is somewhat long. There's also a continuum of how strongly each competitor affects the other. So the ends of the continuum are represented are called commensalism. So if you have a zero interaction on this end, then that's commensalism, and then a zero interaction on this end, that's commensalism. And then in between, there's some level of competition. And then moving on, ecologists have long thought that competition between species was important in communities, and even Charles Darwin argued that it could influence both ecological and evolutionary principles. And there's interspecific competition that can lead to two possible outcomes, both competitive exclusion. In other words, a dominant species prevents another species from using essential resources, and the inferior species may actually become locally extinct. And then there is also competitive coexistence, and this is what is more typical, where both species coexist despite sharing the limited resource. And so you can see in this example on in the panels over here, in the panel A in the figure, this is when the blue line represents when this species is grown alone. And then if you introduce a competing species, you see that the species population growth is reduced. And the same happens in panel B. However, in panel B, you see that when we introduce a second species, the caudatum, the species that we're interested in, can actually become extinct. And then the same thing with the second species, Berseria, can also have this growth curve that we're seeing, the sigmoid growth curve, where it meets its carrying capacity or reduced carrying capacity, and then when you introduce this other species, you get when you introduce the other species, you get a reduced carrying capacity. Experience on these and many other species have led to the competitive exclusion principle, and this states that two species that use a limited resource in the same way cannot coexist indefinitely, and it results in resource partitioning. And so this is when species using a limited resource in different ways are able to coexist. So they partition the resource in different manners. So this can result in character displacement, where two species compete for the resources, and natural selection can favor phenotypes that allow them to partition their limited resources, thus decreasing the intensity of competition. You can sort of see this down in the figure below, where we have species 1 and species 2, and there's quite a lot of overlap. However, because of the competition in the middle part of this, at the left side of the distribution of species 2 and the right side of the distribution of species 1, individuals of either outside of that competition are sort of selected for because they are more successful at reproducing, and so you get a divergence of the two species for whatever character we're talking about. And also, you remember that when we talk about resource partitioning, that in this example, we have species 1 that had a realized niche that was reduced from its fundamental niche because of its competition with these other species. So they each partition this resource 1 and resource 2 into these different components. And then there's this classic example on the right here, where the Galapagos finches, sometimes called Darwin's finches, where character displacement appears to have occurred in two species of these finches on the Galapagos archipelago. Beak sizes and hence sizes of seeds eaten are different on the islands that have both species. So in the Pinta and Marchena Islands, you can see that the beak sizes do not overlap, that they're quite distinctly different. and allows the two species to eat quite different size nuts or fruits. And then on the island where there is only one species, so Daphne Island and Los Hermanos Island, you can see that there's quite a lot of overlap between the two species beak sizes. So we've talked about the Lotka-Volterra model previously when we talked about predator-prey relationships, and so we can now extend this Lotka-Volterra model into interspecific competition, so competition between two species. And there's evidence for resource partitioning has been used as an explanation for the patterns of species diversity found in communities. Mathematical models can predict those outcomes. And then this is the Lotka-Volterra model down below. So it's sort of a modified logistic equation where remember that N is the population size, R is the intrinsic rate of increase, and K is the carrying capacity. However, you can see that in the competition model, the competition coefficients are subtracted to indicate how strong the competitive effect is on one species or another. And so alpha and beta are the competition coefficients, and they're shown here, right? And so this is you actually have a quiz related to this where you're going to work with this figure sum in a table, an Excel table related to this figure, and so you'll be able to see how changing the alpha and beta, the population sizes, et cetera, the carrying capacity affects this figure. One of the things that you will notice, though, is that when you start looking at these models, that the species, for example, A, can never reach its true carrying capacity because it's in competition with species B, and the same for species B. It can't reach its true carrying capacity because it's in competition with species A. And so zero population growth isoclines is the next thing we're going to talk about, and these are the population does not increase or decrease in size for any combination of N1 and N2 that lie on these lines. And so zero growth isoclines can determine the conditions under which species will increase or decrease. So for example, in the panel A, you can see that we're talking about species 1, K1, K1, K1 over alpha. And any time that the line falls into, and these are population sizes, remember, on the X and Y axis, but anytime population falls into this yellow area, it gets pushed back to this line or increased, and if it falls into the blue area, it gets decreased back to this isocline. And the same thing for population B, just that now we're looking at the Y-axis as opposed to the X-axis. And then this graphical approach can be used to predict the end result of competition. So N1 and N2 isoclines are plotted together in 4 possible combinations. I'm not going to go through each of those, but I do want to talk about the isoclines that do not cross. For example, here, A and B, this results in competitive exclusion, and it depends on which isocline is above the other, which species will always be the winner and the other will go extinct. So in this gray area, if the population ends up in this area for population A, it gets pushed back to the line, you end up in eventually having this competitive exclusion where the population of the species A gets pushed to its carrying capacity, resulting in population B going extinct. And then in only one case, this panel D down here, the two species coexist, and they do so although competition still has an effect. The equilibrium of each species is lower than its carrying capacity, however. And so this space right here where they cross is actually the point where the species can coexist supposedly forever, given certain conditions for the environment. Also, coexistence occurs when alpha is less than K1 over K2, and K1 or K1 over K2 is between alpha and 1 over beta. If alpha and beta are equal or close to 1, the species are equally strong competitors and have similar effects on one another. And then also we can think about altering competition. So disturbances such as fire or storms can kill or damage some individuals while creating opportunities for others. Some species can persist in an area only if disturbances occur regularly. So a good example of species that require disturbance are Serotinus plant species that require fire to open their seeds and release their seeds. Also, the fire sort of kills back a lot of competition and allows the species to persist. And then, of course, there are some species, such as raccoons, that do really well with human disturbance and are oftentimes sort of urban pests. We're going to talk more about disturbance a little later and when we get into some community ecology stuff. So with that, we look forward to seeing you guys again soon.